Good afternoon. Shortly, we will hear an interesting lecture by Dr. Amit Finkler on quantum sensing. Dr. Finkler will define what quantum sensing is and explain what advantages quantum sensors offer over classical ones. Moreover, Dr. Finkler will give concrete examples of applications in his research as well as in the industry. This webinar is part of a webinar series organized by Photonics Israel on various aspects of photonics. Photonics Israel operates within the Engineer Association as a cluster of photonics entities. Our mission is to deepen the knowledge in photonics and to encourage cooperation both within Israel and with photonics entities in the world. We are holding a weekly webinars on various photonics topics. We invite you to sign up to follow the activities we hold, which are published in our monthly newsletter. Per your request, the newsletter will be delivered to your mail. My name is Shlomo Glaser. I am the manager of Photonics Israel. With your permission, few words in Hebrew. תראו, בשנים האחרונות יש התפתחות מאוד מהירה בפיזיקה קוונטית וביישומים שלה. הקוונטית מסבירה תופעות שאינן מוסברות על ידי הקלאסית ושאינן ניתנות לחיזוי על ידה, אבל הבנתה מהווה פתח עצום ליישומים רבים, היא מייצרת נדבכים נוספים לפיזיקה הקלאסית והשימוש בה ידרוש מאיתנו התאמה של האינטואיציה ההנדסית. היישומים הם במגוון תחומים, מחשוב ותקשורת, ניווט, גלאים, מדעי תאוצה ועוד. ועבורם יהיה צורך במהנדסים עם ידע מתאים. זו מגמה עם פוטנציאל כלכלי רב, ומייצרת הזדמנויות לתעסוקה והתפתחות אישית. בואו ונלמד את הנושאים האלה. לידיעתכם, אוניברסיטת בר אילן הודיעה כי בשנה הבאה היא תפתח תוכנית שנקראת Quantum Engineering. זאת אומרת, המהנדסים יוכלו ללמוד בתוכנית שעוסקת ומלמדת את הנושאים האלה. אז זו הזדמנות לרכוש, להשביח את הידע ולהיות מוכנים לניצול ההזדמנויות שהטכנולוגיה הזאת מזמנת. דוקטור אמיר פינקלר is a physicist in the Weizmann Institute of Science. He is studying the magnetic properties of molecules using quantum sensor. Dr. Finkler, the floor is yours.
Thank you, Shlomo. Okay, just tell me if you can see my screen.
כן, רואים מצוין.
Very good. And one final touch is the laser. Yeah, okay, so you also see the laser. So greetings, my fellow engineers and architects. My name is Amit Finkler. As Shlomo said, I'm a senior scientist in the Department of Chemical and Biological Physics at the Weizmann Institute of Science. And in the framework of this Association of Engineers and Architects in Israel Quantum Sciences webinars, I'll talk today about quantum sensing. And so to give some applicative engineering problem or challenge, if you will, from industry all the way to fundamental science, I'm presenting you with an MRI cross-section of my brain. And this is really one of the modern wonders of the 20th century medicine, where you can peek into a patient's skull and image the concentration of water in every voxel, or voxel is a three-dimensional pixel, in a non-invasive and a non-harmful fashion. And state-of-the-art machines, which are probably too expensive for mass hospital distribution and perhaps not even certified by humans, so you can get to a voxel size of about 100 microns cubed, and once again, a truly remarkable feat of engineering. But what happens when you want to do the same MRI on such a small molecule? 1 second, I'll just turn off this. So this pointer is, for some reason, not behaving as I wanted to. Yeah, good. So let's ask ourselves what will happen if we want to do this same MRI on a single molecule whose size may be, a few tens of nanometers if it is a large protein. And this is, by the way, this molecule is called cryptochrome. It's a light-sensitive protein, which is part of our sleep-wake cycle. And so the intuitive, and as it turns out, the proper way to tackle such a goal is to use a sensor which is of the same size as the object under investigation. And with this small size feature of a few tens of nanometers, this immediately calls for quantum effects to kick in. And hence our need, or some kind of motivation, for quantum sensors. By the way, note also that the required gradients, so the gradients required here to get these kind of images going from a brain, a whole brain, to a single molecule are also significantly higher. But that's just a side comment. And so another aspect of sensing and metrology is the aim to get devices or sensors which have an increasingly better sensitivity. That's on one hand, and which can distinguish between features that are closely one next to the other, either spatially or spectrally, or in any other axis you can think of, and this is captured in resolution. And once again, when one goes into smaller and smaller feature sizes, one encounters a real barrier to sensitivity. For example, one that is set there by the so-called quantum standard limit, or QSL. And as a quick example or analog, think of the error when trying to measure the number n of raindrops in a certain region on a tin roof. So this can be raindrops, it can be large particles, but the same applies also to if it were electrons or photons. And the quantum standard limit here means that the variance in measuring them will not be smaller than the square root of n. And perhaps you can already guess that this being the standard limit, perhaps we can go beyond it and achieve better sensitivity. And so I welcome you now to the second quantum revolution. And some of you may have heard of this term before, but then the immediate question arises is if this is the second quantum revolution, what is the first one? And the first quantum revolution, of course, is the one sparked by, among others, Max Planck. And now this is the picture of Max Planck close towards the last third of his life. But in 1901, he actually looked more like this when he published his seminal work where he laid the foundations for quantization, essentially postulating that electromagnetic energy could be emitted only in a quantized form, E equals h nu. And so Albert Einstein picked up this line of thought. And as we all know, in his extraordinary year, in 1905, he presented an explanation for the photoelectric effect. And this, followed by Niels Bohr, his model of the hydrogen atom, it led to two equivalent pictures or formulations of quantum mechanics. This revolution, of course, did not end abruptly there, but naturally, I don't have time to go into the details. And actually, it's part of a standard curriculum when studying electrical engineering, and I can attest to that. I studied electrical engineering. So quantum mechanics has really revolutionized our understanding of nature, and first and foremost on the microscopic level. And a prime modern example is a device that many of you own, a device that could not have been created without our extensive understanding of quantum mechanics. Maybe you know what I'm referring to. If not, I'm giving you the inner picture of the newest model. And due diligence, I'm not a share owner of this company. But this is really how the first quantum revolution, or in the 20th century, this is the culmination of this revolution. Right, so as I was saying, we're in the midst of a second quantum revolution, and people are making this distinction because the fact that we understand quantum mechanics, or think we do, did not give rise to devices which utilize the peculiar nature of electrons or photons. For example, and this is perhaps the most mind-boggling example, is entanglement. And the emphasis here is really on the control and manipulation of individual quantum objects. And I'll get to this to define what that is in a few slides. So at least in Europe, quantum technology is divided into these four main subfields. And what you don't see here is that there is a silver lining, there's a thread going through all these fields, and that's the hardware and software. But now talking about the the subfields themselves. I'll give a brief taste into each. So communication, sending quantum key distribution entangled photon pairs via satellites over 1,400 kilometers between China and Austria, also known as quantum teleportation. This is the herald, you could say, of the quantum, what's known as the quantum internet. In terms of computation, you probably have heard about a year ago the announcement by Google about quantum supremacy. So where they demonstrated a computer chip consisting of 53 quantum bits or qubits, and now they are scaling this up, and there's a racing competition with IBM, Intel, and other companies. Quantum simulation, this is an example using what's known as trapped ions. Again, they are more or less head to head with the Google, IBM companies in terms of how many qubits, again simulating many body systems. And finally, sensing or quantum sensing. And here is the artist's rendition of how we do sensing using what I will later show you, known as the nitrogen vacancy center in diamond, or the envy center in diamond. And in this case, it's the imaging of antiferromagnetism in bismuth ferrite of all materials at room temperature. And so industry takes a particular interest in these technologies, and hopefully I'll be able to allude to the origin of this in the next slide. About 4 years ago, I would say, quantum technologies community in Europe submitted a manifesto to the European Commission, which after a lot of politicking resulted in its announcement of a quantum technologies flagship. And that's a $1 billion, and for industry, for academia, that's a lot of money. And here I'll limit in the next, in the remainder of the talk, I will limit myself to quantum sensing. Good. So what's all the rage? What's all the buzz about quantum technologies? So I personally believe it's a combination of what seems to be like a dead end in the semiconductor industry. Although we do see announcements, so this is, I would say these numbers are already not up to date. You could replace the 14 here with 5 and the 22 with 7, but still it's some kind of, it doesn't look like it's going to end well. And so you could say we're reaching the end or the limit of capabilities and making ever smaller transistors. And as you all know, the Internet of Things is booming all around us. And so there's an increasing demand for better and smaller sensors. Hence the idea where these quantum technologies might come in handy. Where you have lots of sensors and lots of devices, you also become more vulnerable to hacking. And so you would want to make them hack-proof or improve their cryptographic capabilities. In terms of simulations, so this comes from academia. The minute you scale the number of elementary particles in your simulation, it really blows. You cannot really simulate it because of the computing power necessary will just not be enough, and quantum technologies can assist in that. And again, from a fundamental point of view, we want to improve our definition and knowledge of the standard metrology standards, such as what exactly is 1 second, how do you define 1 second, how do you define 1 volt or 1 ohm. You might want to overcome the classical limits of noise, and of course, peek into natural phenomena with a new set of tools. We typically concentrate on 3 characteristics of quantum technologies, which are these. So I'll talk about this also in the next slide, but just to give you this in a nutshell. So we need a quantum object. We need this quantum object to be coherent, and we might or might not, it's like an optional feature, use this property of entanglement. And anecdotally, the name of the American project as opposed to the quantum flagship in Europe, the name of the American project is known as Quantum Leap. And if you were born in the 70s like I was, then this perhaps rings a bell. Quantum Leap, very famous TV show. So, all right, so let's consider some more formal definitions of what actually quantum sensing is. I want to give you, like I said, the formal definition. So quantum sensing is the use of a quantum state to measure a physical quantity. It is the use of quantum coherence to measure a physical quantity, or the use or the use of quantum entanglement to improve the sensitivity or precision of a measurement beyond what is classically possible. In the next 3 slides, I will explain each of these properties. But then if you, to every such property, there is a related function or a related criteria that the quantum system must satisfy. And if it has a quantum, if we are using quantum states, then the system will have discrete resolvable energy levels. You will see that later. We should be able to polarize it into a well-known state and read it out. And these are like, you will see this very soon, but these are a must, really musts in this technology. Otherwise, we cannot do all of our manipulation of those quantum states. And finally, not finally, and third feature of the system, we should be able to manipulate it in a coherent fashion. And finally, and most importantly, for a quantum sensor, for a system to function as a quantum sensor, it has to interact with the outside world. So interact with, in this case, a relevant physical quantity, the one that you want to measure. And this is usually quantified by something we call a coupling parameter. But you can think about it as some interaction strength, or how strongly you feel, or your quantum sensor feels the object under investigation. So when I say quantum state, what do I mean? So in quantum mechanics, states represent probability amplitudes. And this is perhaps the main distinction from classical states. And you may have heard this before, but it's important to reiterate this. So classically, a logical bit at either can be at either of 2 states, either 0 or 1. Quantum mechanically, however, the analog of a classical bit, also known as the qubit or quantum bit, may be in a superposition between the 2. So these 1 and 0 are the possible outcomes. But as long as we don't measure, before we measure, they're represented by a probability amplitude. And as long as we don't measure, like I said, it may have some probability to be in the first outcome, and an unfinite probability also to be at the second outcome. So we define this formally in the following way. Again, there is some kind of amplitude, probability amplitude to be in 0, but it's also at the same time, and this is important, at the same time can be also at the second outcome. And because it's a probability amplitude, there is a strict constraint on the probability amplitudes that everything is normalized to 1. And this is perhaps best exemplified. You probably all know Schrödinger's cat. So it's a good thought experiment of how something can be both simultaneously at 2 states. And it goes to show that as long as you don't measure, the probability can be in a state which is physically it's not possible. So the cat cannot be both dead and alive. But that's because we didn't look into the box. We didn't see, we didn't measure. So this is perhaps the biggest or the most significant difference from classical physics. All right. So that's what we define as a quantum object. Quantum coherence. So it's perhaps more tricky to explain, but you can think of it as the time it takes until the information about the system is lost. So it's kind of, people call it sometimes phase memory time or memory time, but as opposed to a classical physics, this memory time or phase memory time or coherence time is on a single quantum object. And why is this time finite? it's related to the object's potential as a sensor, or in other words, its coupling to the environment. So the stronger the coupling is, the shorter this coherence time will be. And one of the main themes or in quantum sensing is to try to extend this coherence time with as little harm as possible to its sensitivity. So if you have a long coherence time, you can do more sensitive measurements. But the opposing actor in this game is that if you want to, the environment itself might cause a reduction in this coherence time. So that's quantum coherence. And if coherence was tricky, entanglement is really something else, because this term really has no classical analog. An example is so for those of you who are from the photonics or optics field, you can there's a good example, and it's what is known as the spontaneous parametric down conversion, or SPDC, in a BBO crystal, where the state of one photon is tied or entangled to that of the other. And in sensing, we can make use of this unique quantum property to further improve the sensitivity. So when I say entanglement, what do I mean? It's related directly to the fact that I mentioned before, that the wave function, this probability wave function, can in principle consist of contributions from all possible outcomes of the measurement. In this case, it's a simple 0 and 1, but it could also be many such qubits, or a quantum system which consists of more than 2 states. And then the fact that they are entangled, it means that we call this in the community quantum parallelism, and it's a result. This is in a way what leads to what we call a quantum phase estimation. So if you have a smart way of going about and realizing from the outcome of measuring such a highly entangled state in which state you're in, then you might have saved yourself a lot of time. And so in the scope of this introductory talk, and as I said, we're focusing on sensing and metrology, I'd like to give you some insights as how we can use quantum mechanical effects to go beyond the classical limits. So in general, and I'll show you this in detail in a few slides, one of the defining properties of a quantum sensor is its extremely high sensitivity to its environment. And in fact, this is the other side of a much more sinister coin, and that's the sources of decoherence. And what we typically do in these cases, we're banking on the vast knowledge and indeed standing on the shoulders of our peers from the magnetic resonance community, and that's to try to decouple all sources of decoherence except for the signal we're interested in. And these methods are also known as dynamical decoupling. And if you want some intuition as to understand what dynamical decoupling is, try to think of a motor of an airplane. This is a propeller, and I'm not sure if you see this. Yeah. So you see the propeller rotating, and it was not rotating in its actual speed, right? So this was a stroboscopic measurement of its motion. So you were able, like I said, to decouple this image from all other sources except the very frequency you were interested in, and that's why it resulted in this very slow rotation. So this is in a nutshell dynamical decoupling. But this is not the ultimate limit in measuring. So it has been shown that one could reach the so-called Heisenberg limit, and that's going. So this 1 over square root 2 is analogous to the square root n you saw before of the noise in measuring raindrops or electrons or photons. And it has been shown that, and this is the standard quantum limit, and one can go further than that to what is known as the Heisenberg limit and achieve a lower noise level. And in this case, to do that, people use what's known as error correction or quantum error correction. I'm not going into this today. This is perhaps the subject of next week's talk or the talk in 2 weeks. But this would not have been possible. This is not possible with the classical system. That's what I want to emphasize. And another well-known example is squeezing. So one of the earliest definitions of that is the following. So the signal that one wishes to detect is encoded on the field variable with reduced fluctuations. What do I mean by reduced fluctuations? So this is another direct outcome of quantum mechanics. It stems from Werner Heisenberg's uncertainty principle, which is a fundamental property of all wave-like systems. And remember, we're talking about probability waves. And it states that the fluctuations of two conjugate variables, such as position and momentum, cannot go below a certain value. And here, the name of the game is to play with those fluctuations. So you see here that what they did is you play with fluctuations in one axis, and you kind of squeeze them. But on the other axis, because of this uncertainty principle, the fluctuations actually increase. And if you can focus your system or make use of only the fluctuations that you manage to squeeze, then you may gain in your sensitivity. And this is actually being used in the detector called LIGO, which was used to detect black hole in the center of our galaxy. Right, and it's also captured by this acronym. And if you read Robert Heinlein's "The Moon is a Harsh Mistress," you would know that this stands for "There ain't no such thing as a free lunch." So if you squeeze in one dimension, you'll have to get an elongation or increase in the other conjugate variable. All right, so we can continue now to quantum sensors, and in a wider sense, quantum metrology. So one can measure various quantities, the most advanced of which is time or frequency, where usually people use an atomic vapor of alkali atoms, usually it's cesium, but sometimes others, rubidium and others. And the cesium, for example, the atomic vapor in cesium now is what is known as the standard of 1 second. One can also use quantum sensors to measure temperature on very small length scales, and also the relative gradients. And finally, and this is what I'll elaborate in the next, in the remaining part of the talk, is the possibility to detect minuscule magnetic fields, which are orders of magnitude smaller than Earth's magnetic field. And so the quantum sensor we work in the lab is called the nitrogen vacancy sensor in diamond, or simply the NV. It consists of a nitrogen substituting a carbon atom next to a vacancy in the diamond. And compared to this Cullinan diamond, which is a natural one and was dug up about 115 years ago in a mine in South Africa, weighing a whopping 600 grams, it was the largest gem quality diamond ever discovered. And so our diamonds are typically 5 orders of magnitude lighter and are grown atomically, layer by layer, that is synthetically, in the lab. And for the experts among you, we are talking about chemical vapor deposition of single crystal diamond. And so the defect I mentioned before, again, is a nitrogen substituting a carbon next to a vacancy. A vacancy is a lack of a carbon atom in the diamond lattice. And because it's really atomic in nature, it's almost by definition, it is quantum. So one of the most distinct features of this defect, this NV defect center in diamond, is the red hue it gives diamonds. Diamonds, that is, that have a large concentration of them. And here is an example in this image of such a diamond. You can ignore the green light, it's some artifact from the camera. So when illuminated with a green laser, you see that is unquestionably, it emits red light. And if you put a red filter in front of the camera, you really see the red fluorescence. And I will use this opportunity because this, if we were in a real talk, in a physical talk in an auditorium, I would not, because of safety reasons, I would not be able to do what I'm doing right now, but I'll do a live demonstration. So it will take me 1 second, set it up. So I'm putting a red filter in front of the camera. Sorry. I hope you see. I'm putting on safety goggles for myself. I have a laser. So this is a green laser. And I have a diamond. So this is this diamond. I'm picking it up right now. So here's the diamond. And I'm going to shine this green laser on it. So if you see the green laser, it's hitting my fingers, hitting various parts of the tweezer. But then when I hit the diamond, you see that it fluoresces in red. Okay? And this fluorescence, and I'll show this now in the next slide, is the unique property of this quantum sensor. Right. We can continue. All right. So by itself, this red fluorescence is not something unique. You may find other stones that fluoresce in red. But remember that what I talked about earlier. So in order to have a quantum sensor, we need discrete energy levels. And what do I mean by that? In the case of the NV center in diamond, these energy levels are its spin state. Now, this is not related to political spins, which are very common today in Israel, but rather to an internal degree of freedom the system has. It behaves very similarly to angular momentum. And historically, it received, this is the reason it received this name spin. Actually, there's nothing spinning in there because it's a quantum mechanical property. But for our purposes today, you will need to accept its existence and that indeed it offers these discrete energy levels. So the NV center, it has three discrete energy levels. So this is, we name them 0 and plus and minus 1. They're small, almost separated by almost nothing here. So there's a little dashed line, but the full line, the full blue lines are the +1 and the -1 line. So you have 3 lines, +1, -1, and 0. And in our setups, in our experimental setups, we usually excite the diamond, as you saw, with the green laser. So we do this, and we measure the red fluorescence it emits. Now, the striking feature of this sensor, this NV, is that the red fluorescence depends on the spin state. So it's a quantum mechanical property, and depending on the state of this quantum mechanical property, the fluorescence will be different. And this is a bit mind-boggling because we're talking about a single atomic defect in diamond. And you will be able to see the difference in the red fluorescence, whether you're at 0 or at ±1. All right, so this is not only that, I mean, so this is one property. You have more fluorescence if you're at 0 and less fluorescence if you're at ±1. But not only that, because also if you start, whether you start at 0 or you start at ±1, and by the way, to get from 0 to ±1, you just apply a microwave energy. So you take your favorite microwave synthesizer from various companies, we use all of them, and irradiate with an antenna, irradiate the diamond, you will be able to jump from 0 to ±1. But what I'm trying to say is that whether you're at 0 or at ±1, you will preferably return back to 0. And this is the property I was talking about, which is polarization. It means that in effect, this green laser, what it does, whether you're at 0 or at ±1, you will return all the way back to 0. So we have a fantastic way of polarizing the NV. And so we have a quantum object. It is a single spin, single quantum mechanical object, or state, whose state or spin state we can gauge by optical means, and we can manipulate its state by microwave irradiation. So this dip here at around 2.68 gigahertz is the separation between this 0 and either the plus or the minus 1. And when we apply a magnetic field, and that's the interesting property, this degeneracy between the 0 and plus minus 1, it splits. Okay, and this is due, again, for those of you who know the term, this is the Siemens Effect. So this is quite remarkable. So you have one quantum object, and remember, this is a single atomic defect in diamond. It can tell us, quote unquote, it can tell us what the magnetic field it feels by just measuring the splitting. So I just look at the dip here. I look at the dip here. I can measure frequency very well. I know what the frequency difference between the two. And from this, I can back calculate and tell you what the magnetic field it feels. Okay? So if we focus on only one of those dips, we have, in essence, we have a single quantum object, which we can initialize. Initialize that is the same as saying polarize. We can manipulate it. We can read it out. And this is what exactly we call in our community a quantum bit or a qubit. And another way to visualize this graphically, we like to visualize qubits in a geometrical manner in this sphere. It's also known as the Bloch Sphere. And I'm showing this, first of all, because I want you to get a feeling as to what we're doing sometimes on a daily basis in the lab. And second, since it's also a very good graphical illustration of quantum sensing. So 0 and 1, the same 0 and 1 from before, are at the north and south poles of the sphere. And I remind you that we know how to well polarize the NV to the 0 state, and that's this black arrow coming from the center upwards. And I'm giving now an example of how we do a single spin manipulation or single state manipulation, and how we can encode the magnetic field onto the phase. You will see what this phase is. So one begins by applying a microwave pulse, which projects the state to this superposition. So now it can be at either with equal probability at 0 and 1. So this is the graphical representation of that is we project it to this XY plane, which is in the middle, halfway between 0 and 1. And then what happens is that magnetic field sensing commences, and due to this interaction of the spin with magnetic field, it starts to acquire some kind of a phase. All right, so it's still at the XY plane, but now it's no longer at the XZ plane in this projection. It acquired some phase phi, and this phase is exactly how we encode the magnetic field this sensor feels. And with another pulse, with another pulse, we project it back to either 0 or 1, and we measure. And this is this example of how we do magnetic field sensing. So essentially, we have everything. We have a way to, like I said, initialize, manipulate, read out, and even encode information that is interact with the external environment. And all we have to do now is, if we want to improve upon things, is to devise more and more sophisticated schemes to get the signal to be encoded onto this phase and have all the unwanted information, well, not there. And by the way, we define here, it's very easy to define coherence, because coherence is our ability to determine what this phase, what this relative phase, relative meaning relative phase between 0 and 1, what this relative phase is. So next, I want to give you two or three examples using these quantum sensors to detect magnetic phenomena with high sensitivity as well as high spatial resolution. So first is a study that I led about 3 years ago, which involved sensing magnetic signals from a single-digit number of peptides. Peptides are very similar to amino acids. They're just more synthetic in nature. And in general, they carry no component which can lead to magnetism. And the trick is to label them with others. So the peptides are these long things over here. And the trick is to label them with smaller molecules, which are magnetic, and then sense those molecules with very high precision. And the result is the possibility to understand what's going on in terms of structure and dynamics of the original peptide by measuring the signal from these labels. And so here the solution of these peptides was placed directly on the surface of the diamond, and we were able to detect not only those labels, which are called spin labels, but also we were able to gauge the interaction between pairs of them on the carrier peptide. And this is something that if you want to do this on this very small amount of molecules, you have to use these quantum sensors. Another fine example, and this time not by my group, but by colleagues in France and Switzerland, is of looking at the magnetic order of an antiferromagnet. So here what they did is they fabricated small diamond cantilevers, you see this here, with the quantum sensor embedded in them, in this pillar, and this acts as a scanning probe microscope, and they use this microscope to scan over a material. In this case, it was bismuth ferrite. It's an antiferromagnet. Antiferromagnet is a material where neighboring magnetic domains have the opposite magnetism. So instead of a ferromagnet, all the domains are pointing in the same direction, and you have, so iron is a very well-known ferromagnet, but in an antiferromagnet, the neighboring domains are pointing in opposite directions, and therefore the overall or total magnetism is very, very small. The signal is very small, and again, using a quantum sensor makes it possible to sense this property with high precision, with high sensitivity. Good. Next, I want to give you an example or several examples of where this where we're going, where this quantum sensing is going in industry as of now, 2020. So, as I said earlier, the most advanced and accurate to date quantity we can measure is time or frequency, and quantum sensing of it has only improved the precision. And as you know, time is of the essence, but it is also a critical parameter in satellite navigation, for example. And so you can imagine that companies, including semiconductor manufacturers, laser producers, and of course, Israeli entrepreneurs are already on it. So that's sensing of time. Gravity, so sensing of gravity may seem trivial, but now imagine the different possibilities if you can tell how massive each square meter of the Earth is when deciding on where to dig and how deep to dig and what lies beneath the surface before you start digging. So both time and gravity make heavy use of these atomic vapors I was talking about, and an arsenal of state-of-the-art lasers. Now rotation. So rotation is maybe a simplified word for gyroscopes and navigation, of course. And this I think I don't need to explain why these are of interest to various companies. And if you look at the names I listed here, you can also deduce what the application is. In the case of Bosch, for example, a small company in Germany. So this is related again to Internet of Things in cars and other utilities. And finally, related to my lab's field of research, so magnetometers of various sizes and uses are all around us, and some really heavyweight players throughout the world are now entering the scene, mostly for medicinal and biotechnology applications, but not only. And finally, there's even another example where Lockheed Martin introduced a gyroscope earlier, about a year ago, in a press release. And this is a detector or a gyroscope which uses diamonds. Right. So before the chaos we currently have in our government in Israel. So the state of Israel decided to invest in quantum science and technologies. And this program, headed by Tal David, whose webinar you might have attended last week here, the program seeks to utilize the second quantum revolution into applications. And I will give you such an example in the next slide. So if you recall, we're sometimes interested in finding out what this phase is. And the problem with these small quantum objects is that sometimes the signal coming out of them is small, or simply a small signal to noise ratio. And here too, methods which I learned some 20 years ago in my electrical engineering classes, they come in handy. And I'm referring to Bayesian estimation or statistical inference. And so together with an Israeli startup, we're currently conducting an experiment whose aim is to perform these Bayesian updates in real time on the quantum object, the NV Center in Dynamic. So as I said, this project is funded by the Israel Science Foundation and the Administration for the Research and Development of Weapons and Technological Infrastructure. So again, this is a very nice example of how we use hardware which was tailored and built specifically for quantum systems in order to increase the sensitivity of a quantum sensor. All right, so I think it's time now to summarize. I hope I gave you a glimpse into quantum sensors in this quantum technologies world. And I hope I was able to convince you maybe a bit that they do have an edge over classical counterparts, both in terms of when you're looking at small objects, so when quantum effects come into action, and both in terms of the potential of using their so-called giddiness or disentanglement property. And I also showed you that they have wide applications in both academia and industry. And I would like to summarize with two quotations from Niels Bohr, one of the fathers of quantum mechanics. So those who are not shocked when they first come across quantum theory cannot possibly have understood it. And second is that if anybody says he can think about quantum problems without getting giddy, that only shows he has not understood the first thing about them. Thank you.
Thank you very much, Dr. Finkler. Very good, very interesting lecture. It's time for questions. So don't hesitate. Just ask Dr. Finkler your questions. Don't be so shy. Well, people have to maybe to think about it, and maybe
we always said that if there are no questions, either everyone understood everything or nobody understood nothing.
Yeah, but thank you very much, and we hope to hear you again.
Thank you.
Okay, goodbye. Thank you.
Bye-bye.